Okay, so last time we talked about constant velocity, and we ended up with pretty much this formula. Uh, Displacement final is equal to velocity times time plus displacement origin, or initial. But now it's time to up the ante and talk about constant acceleration. And we're using our basic acceleration formula, that acceleration is equal to a change in velocity over a change in time. And we can do the same thing we did before, where we talk about a graph, and that graph having a straight line, and this time it's a velocity versus time graph. So now that it's velocity versus time, we could say, oh, then my rise over run, my rise being velocity, my run being time, so my slope for that would equal an acceleration. But there's other ways to do it too, and we get way more formulas for constant acceleration because we need them in order to do all of it. Notice we're going to end up with 4 total. Now, the first one that we get, I'm going to show you 2 ways to get it. First of all, we could do the rise over run the same way we did constant velocity with constant acceleration, and we can come up with basically the same type thing but with acceleration. So you'd say V final is equal to V initial plus acceleration times time. Now I wrote it slightly different. I put the initial velocity, instead of adding it at the end, I added it at the first. It doesn't make any difference with order of operations. The rest you can't really get from the graph as easily. There is a way, but we're going to use calculus. And I want to show you that they come from somewhere, so I'm going to show you how to calculate this one and the second one. And you can just trust me on 3 and 4 that you can do that as well, because you don't actually know how to do calculus for this class. But first thing I'm going to do is I'm just going to show you all 4. And I want you to write them down 1, 2, 3, and 4 in the same way that I'm writing them, because we need to be able to refer to Formula 1, Formula 2, Formula 3, Formula 4 for constant acceleration in kinematics. We're going to use these a lot, and they're beyond what you would probably just memorize. So our next one, and so like I said, I'm just going to write these out. It's a little bit more complicated, but it is d final is equal to d initial plus velocity initial times time plus 1/2 of acceleration times time squared. Our next one, number 3, displacement final is equal to displacement initial plus velocity final plus velocity initial divided by 2, it's in parentheses, all multiplied by time. And our fourth one, velocity final squared equal to velocity initial squared plus 2 times acceleration times basically the change in displacement, so df minus di. Okay, so take a look at these. Make sure you have all of these down and in the proper order. This is 1, this is 2, this is 3, this is 4. We're going to need to use these over and over and over again, because this is how we'll be doing all projectile motion. So if you need time, pause this video here and copy them down. So why do we need all these formulas? Because you get constant acceleration far more than you do constant velocity. Think about just a simple scenario. If I stood on a cliff and I dropped something like my cell phone, pay no attention to the annoyed look on my face and the "we're done," but say I dropped my cell phone off a cliff. Well, I can't use a constant velocity with that because it doesn't have a constant velocity. It starts with a velocity when I let go of it of 0. So right here, the velocity, initial velocity, is equal to 0 meters per second. And yes, it would be downward, but you don't have a negative when it comes to 0, so we just say 0 meters per second. But you know that it's not going to stay still in the air. It's not Wile E. Coyote running around on a cliff going whoop, 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 whoop. No, it's going to start to go downward. That means that the velocity is changing. So that formula we learned for constant velocity wouldn't cut it for even measuring dropping something. But it will have a constant acceleration, because think about what is accelerating it. What pulls it down towards the Earth is gravity. With gravity, we have both a force and little g, as we're looking at right here, is the acceleration due to gravity. And that's 9.8 meters per second squared, which, since it's squared, we know from this unit that it's an acceleration. Notice meters per second velocity, meters per second squared, acceleration. So that means my cell phone would constantly be changing velocity in the downward direction, because we also know that this is negative by convention most of the time. Straight down, that's usually going to be negative. All right, so that means we need something that has a constant acceleration that can calculate these things. And if I just wanted to know how much it was going to change in velocity, I could use that first formula. So I could use that one that is my velocity final is equal to my velocity initial. Remember, these are all vectors. And then I'm going to add to that my acceleration times time. And all I really need, since I know little g, is I need to know the amount of time, because I know VI. Remember, it was 0. Acceleration, I know that, negative 9.8 meters per second. So let's just say 3 seconds. So here's my cell phone 3 seconds later, and we want to know its velocity there. Then all we have to do is we go, well, it started at 0 meters per second. We're adding to that a negative 9, let's do a better 9, a negative 9.8 meters per second squared. And we're going to multiply that by 3 seconds. And you're going to figure out that that velocity final is now, well, first of all, it's a negative number, because that's negative, and we didn't have anything to cancel out. So negative 3 times 9.8 is 29.4 and meters per second, because remember, with our units, those seconds is going to cancel out one of those seconds, so we end up with just a velocity. So yay, that seems useful, but remember, that's the one we can get from a graph. But this becomes immensely popular, even if I was to throw it upward. So let's say I took my phone and I threw it upward. As soon as it leaves my hand, I can't accelerate it upward anymore. So it's not going to be accelerated upward. It has an upward velocity, but it's going to be slowing down constantly, because the constant acceleration is going to be gravity. The only way with projectiles you end up having not a constant acceleration is if you have a rocket engine on it, which does add a whole different dimension of difficulty. That's why this technically is not rocket science. Nope, this is just kinematics. But you have to know this before you can do rocket science. So I like to say it's the beginning of rocket science. Anyway, that's enough for this time. Next time, I'll show you how we get 2 of those formulas using calculus. Woo!